Hello everyone, I am Prajwal and I'll be talking on the non-recursive solution for the Tower of Hanoi problem. First things first, the problem statement. We are given a set of three pegs and end disks with each disk being a different size. We can name the pegs as A, B, C or source, destination and auxiliary as desired. At the onset, all end disks are on peg A or the source peg arranged in increasing order from top to bottom. The simple goal of this problem is to move all end disks from peg A to B or C depending on our destination peg. The two simple rules to follow would be we are only allowed to move one disk at a time, and this disk has to be the topmost of a peg and has to be placed on the topmost disk of any other peg. And no disk may ever rest upon a smaller disk, that is, three may never rest upon two or one here. Here's a small demonstration of the Tower of Hanoi problem. Let's start with three pegs. One important thing to note about Tower of Hanoi is that the minimum moves or the most efficient ways to solve is 2 per n minus 1, n being the number of disks. So for 3 disks, it would be 7 moves. So to solve it in 3 moves, we would do it in the following way. Move this here, this one here, and this one here, and this one here. So we did it in 7 moves as seen. Let's try it out for 4 disks. So we would do something like this. This one here, this one here, this one here, and this one here, and finally. So as we can see, we did solve it, but we did like go over the limit for the minimum number of moves. So let's see if our algorithm can help us solve it in the minimum number of possible moves. So our non-recursive solution for the Tower of Hanoi is in the following way. It uses the data structure stack. The main function declares three stacks representing the source, auxiliary, and destination pegs. It initializes the source peg with the n number of disks as given by the user. The transfer function is a helper function which is used to transfer a disk from one peg to another peg. It uses two stack objects as the arguments. The algorithm is such that it iterates through the required number of steps that here that would be 2 per n minus 1, as we saw that is the minimum number of steps required. During each step, it determines the disk which is to be moved based on the current step number and the parity of the number of disks. We split the algo into two parts. That is, when the number of disks are even, we move the disk first from source to auxiliary, then from source to destination, and then from auxiliary to destination. If the number of disks are odd, we move them from source to destination, then from source to auxiliary, and then from destination to auxiliary. So let's look at code here. Here I have a C++ code. We have declared the prototypes for the stack functions. Here we have the class stack, the array, the stack pointer, the name. Is empty simply returns true if the stack is empty. Is full returns true if the stack is full. We have the push and the pop functions. And then we have the element. It simply returns the topmost disk or the element of a stack. Capacity returns the total size of the stack. Set name is used to set name to the stack, and get name is used to get the name. The helper function transfer is basically used to transfer disks from one peg to another. It basically takes two stack structures as inputs and transfers them accordingly. It has a function to check if S1 is empty, it will pop from S2 and push it onto S1. If S2 is empty, it will pop from S1 and push it onto S2. And similarly, if both have a element, it will check for the bigger disk and then push it onto a take the smaller disk and push it onto a bigger disk, whichever peg satisfies the condition of the game. And then we have the main function. We declare three stacks, we name them, and then we have a input for number of disks from the user. We initialize the source with the input number of disks, and then we calculate the number of steps required. As seen, it was 2 per n minus 1. So we run a loop from 1 to the number of minimum steps required, that was 2 per n minus 1. So as we saw in the algorithm, if there were even number of disks, we first transfer source to auxiliary, then we transfer from source to destination, and then we transfer from auxiliary to destination. Similarly, if there were odd number of disks, we would transfer from source to destination, source to auxiliary, or destination to auxiliary. We repeat this loop until we reach the all the disks are arranged properly on the destination peg. So let's look at the program. So let's apply 5 and we can see that it gives us all the steps required. Given we couldn't solve the 4 disk problem, let's see if we're able to take help from the program and do it. So it says us to move one from destination to first auxiliary, two from here to here, this one from, and this one from here to here, this one here, one from there to auxiliary, this four to destination, and then one from auxiliary to destination, two from auxiliary to source, one from destination to source, this one over here, this one over here, and this one here. So as we can see, the algorithm did help us to finish the problem in 15 moves, which is the minimum required. And coming to the time complexity, it would be O to the big O of 2 power n, the algorithm, as it requires 2 power n minus 1 moves to solve the puzzle. Each move involves a constant amount of work. So yeah, the time complexity would be big O of 2 power n. And the space complexity of the algorithm is O power n, as we are only using n number of disks. So we don't occupy any variable constant here. Thank you.